Uh, so today what we're going to cover is to conclude the week, we're going to cover the methodology called difference and differences. I'm sure everyone is at least probably ranges from their familiarity with it, from having heard of it or maybe sort of having a vague understanding of it to having done, having worked with the method a lot. So we're going to be discussing it today. I'm going to take you through both its historical use and as well as some of the changes that are happening with it at the moment. So let's get started. Let's see. I'm going to study covariates, differential timing, phasing units, studies. Yeah. Okay. So let's get started. So difference and differences. Where does it start? It's funny. I've always thought it started with a man named Jon Snow, but then yesterday, a friend of mine pointed me to actually an earlier use of it by about 5 years in the United States. Excuse me. What's interesting is both examples, though, Jon Snow as well as another gentleman, they were using difference and differences about 60, 70 years before the discovery of physically randomized experiments. They were using it to provide evidence for much needed policy changes in their communities. Jon Snow for his work on cholera, and the other gentleman is named, give me 1 second. His name is, what's his name? I can't remember it. But he was studying the spread, the mortality that was happening in hospitals after childbirth. And he was blaming the fact that nobody washed their hands, and everyone disagreed with him. Both Jon Snow as well as this other gentleman were basically trying to overcome theories about disease transmission. And so it's really sort of interesting. We usually think of difference and differences as we don't really associate it with health policy. And it's like, kind of founding like that. It was oftentimes used in labor economics, but in fact, it was developed for trying to postulate both the spread of disease as well as suggest solutions to the spread of disease. It's pretty interesting, but let me tell you about Jon Snow. So Jon Snow was a practicing anesthesiologist in the mid 19th century. He was famous because he had invented a machine that would carefully deliver an anesthesia called chloroform to patients consistently in such a way that they would not that the chloroform wouldn't kill them. That was part of the problem at the time. The chloroform was very dangerous and had to be applied to the patient very carefully, very consistently, very slowly, and they didn't know how to do it. And Jon Snow invented a machine that did it. Basically reduced mortality from surgeries that were being caused by the anesthesia as opposed to the surgery. But now he's famous for providing evidence that cholera was a waterborne disease during the 1854 outbreak. And he published 2 works on cholera. There was an essay in 1849 and there was a book in 1855, and he died of a stroke. Uh, three at the University of Chicago named, I think it was Thomas Coleman. And it shows daily cholera deaths in London. And you can see right here that what is it you see with cholera? Cholera is a lot like COVID in that it can just sort of come out of nowhere and have explosive levels of mortality that just happen almost instantly and then just taper off. And it's very frightening because it is quite painful and has a very high death rate. So cholera will attack you suddenly. Your body will push out water through vomiting and acute diarrhea, extremely painful symptoms, and that will continue to happen until you die. And they didn't know the treatment for it back then. You could have treated it with a tremendous amount of water intake, but in the experiments that they did, they never actually would give the treatment group enough water, and so they never did discover that. Basically, cholera hits London in 3 separate massive epidemics. There was one in 1831. There's one in 1848, and there's one in 1853. And Jon Snow is going to work in all of them. He's going to work at this period of time here, kind of learning a lot. Hold on one second. He's going to be working a lot, treating patients. I mean, he was a doctor but he's also during all 3 of these beginning to devise, just through observation and collection of evidence, some explanations that he didn't think people knew. So 19th century London was a very grotesque city in terms of hygiene. It was filthy. Waste collected in cesspools under houses. It emptied into open ditches, and it emptied into sewers that were not covered. A lot of the way the city was organized, they just didn't have the ability to dispose of waste very efficiently. So it's very early time in industrialization and just the beginning of trying to deal with having cities that were just so dense and so large. So the majority opinion about disease back then was a theory called miasmas. And miasmas hypothesized that disease transmission was caused by vapors and smells. It's unclear about its relevance for spreading disease person to person, but the thing that we do know was that they really thought that disease was being spread by odors. Hold on one second. Get in here, come on. They really thought that the disease was being spread by odors. They just didn't know. That was it's not a ridiculous theory. The odors are correlated with the disease transmission mechanisms, and a lot of the treatments that for the odors would have also affected those underlying mechanisms as well. So there were microscopes back then. Jon Snow actually does get a microscope at one point, but their resolution was very poor. You couldn't really see a whole lot with them. The advances in optics were still to come. So most human pathogens can't be seen, and so no one had ever seen a microorganism before. They didn't know about germs or viruses. Because you can't really. It's hard. It's hard to postulate theories like that about things you've never seen and have no way of proving. A book by Stephen Johnson writes that he does get a microscope at one point, but it's so blurry that he can't really see anything with it. So they wouldn't actually isolate microorganisms for another half century. There were a couple of people, though, that did not believe miasmus was the cause of cholera. And you have to kind of understand, these weren't just people, kind of with an alternative theory, like just sort of they weren't being academics. They really thought that the problem was that the city was focused on the wrong things. By focusing on vapors and odors, they were missing the spread entirely that they said was coming through the Thames River, a river that runs through London. Jon Snow had a theory, and it's amazing because it's essentially accurate. He says that it's not being caused by odors. Rather, there is this organism, an active agent, that enters the body through food and drink and goes into the stomach, multiplies, generates poison, and then the poison causes the body to expel water. The body expels the water through diarrhea and vomit. And that continues until the person perishes. But that's not really enough to explain that. That's where it becomes more social science. Jon Snow says that not only is it this organism, but as the human expels water, and given that London is organized the way that it is with its sewage system, the organism is passing out of the body and going into the water supply. And Londoners drank their water from the rivers. And so they were basically drinking the water from the Thames River and getting infected even more, and it was causing these kinds of epidemic waves. Process repeats itself, growing into an epidemic. So imagine you're Jon Snow and you want to convince people that cholera is spread through the water, not caused by these pockets of air. There's a lot at stake. A lot of people are dying. You might run an experiment. You might run a physical experiment. Maybe what you do is you go throughout the city, and half of the city is going to receive water from the Thames River, and half of them are going to receive water from some other supply source that's not the river. And then you could just observe the mortality rates between the two groups of people. Jon Snow didn't have the ability to run that kind of experiment back then. Many of us don't have the ability to run physical experiments. They may be unethical to people that make decisions. They may not be practical. It may just be really unrealistic. And that's how it was for him. Not to mention that the physical randomization, of treatments being used to isolate causal effects was still 75 years away. But that's not the reason that we have thought experiments. The main reason that we have thought experiments like this is to suggest to us what we should be looking for. It tells us there might be natural experiments that we could exploit. So Snow is I highly encourage you. To study Jon Snow's reasoning. Either maybe read his book or just kind of, go over the article by Coleman or the book by Johnson. And just listen to how Jon Snow goes about trying to interact with the medical profession as well as the policymakers in London. He produces a book, right? That's very natural to an academic. All of us on the line probably can identify with that kind of thing. What do we do when we want to try to convince someone? We write a paper, we write a book, we do some research project. It wasn't just that he wrote a research project. What was the interesting thing to me about the book was the way that he made his argument. The rhetoric of the book is what I find so inspiring. It's very descriptive. He just describes facts about these deaths and facts about the spread of disease historically in London. He discusses case studies. He discusses anecdote. It's just simply a collection of facts. Then he just presents a beautiful data visualization. As you heard me yesterday when we were talking about the importance of visualizing the reduced form, visualizing the first stage, he produces visualizations. And it's not just simply pictures. It's not just simply maps. He's going to produce visualizations that are suggestive of causal effects. All right, that's the thing you want to kind of remember. Pictures that communicate causal effects. And then he's going to finally conclude with a difference in differences experiment. So the observation, how does that look? He observed the progression of the disease for years. You remember, the disease hit London 3 different times, and he focuses on it. He collected a lot of data about the spread of the disease early on. At one point, before an epidemic actually hit in the 1930s epidemic, he actually managed to find the very first person to get infected in London. It was incredible. The amount of work that the amount of Jon Snow really is the patron saint of social scientists because of just the sheer amount of effort and patience that he showed, as well as just the willingness to collect all sorts of data to help make his argument. He noted that treatments didn't work. He would cover people with burlap sacks, nothing would happen. He also notes strange patterns, higher deaths in close proximity to a public pump on Broad Street. He just goes on and on about, describing what we know about the spread of the disease. Then there is this discussion about an outbreak, a particularly bad outbreak in the 1850 period, 1854. He writes, "The most terrible outbreak of cholera which ever occurred in this kingdom is probably that which took place in Broad Street, Golden Square, and the adjoining streets a few weeks ago. Within 250 yards of the spot where Cambridge Street, which is now called Lexington Street, joins Broad Street, which is now called Broadwick, there were upwards of 500 fatal attacks of cholera in 10 days. So how does he argue for what is it? So this is just a description. This is just a description of the outbreak. Okay, so he's just describing the outbreak, but Jon Snow thinks he knows why the outbreak happens. And to convince people of that theory, he produces a map. It's a famous map. Interestingly enough, it's on my wall right now behind us. The lights. Let me see if I can't. See if you can't see it. There it is right there. That's the Broad Street map. I'll show you a close-up picture of it right now. So he produced that map. This is beautiful, famous maps. One of the most famous maps in social sciences and data visualization that's ever been created. It's probably the most famous one in the social sciences. He was looking for the source of the outbreak that happened in that short period of time, but he wasn't forming his theory. He already knew what he believed. He just was collecting evidence that he thought would convince the reader. And here's the map. So let me just show you this. So I'm going to walk you through a couple of pictures here. Pump, 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 pump. These are public pumps. These are wells. These are water, like water faucets that anybody could come to. And they were all over this area. They were everywhere. Pump. But then this one right here is the one I want you to focus on. That's not very good. Right there. What is that? That's the Broad Street pump. Okay, that's the Broad Street pump. And the Broad Street pump, was a pump on Broad Street. There it is right there. It's a pump on Broad Street. And what's unusual about this pump is it's the only pump that has deaths all around it. Right. So notice, you know, in this close proximity, we see a lot of deaths right here. Right. We see a tremendous amount of deaths that are happening right around this pump that aren't happening elsewhere. Okay. And there's lots of interesting things that are going on in this pump. So first of all, let me just sort of point out the elements of the map. Obviously, it's a map of the city. So he must have gotten this shape file from the city. But the other thing about the map is he lays on top of the map of the city these little black lines, right? So he's got some sort of shading that he's doing. These are perfectly made, each one equaling a certain number of deaths. And so he shows you exactly where the deaths are. And but the other thing is, notice the deaths are in close proximity to the pump, but not always. Not always. If you look right here, notice that one, there's no deaths, right? So at the brewery, directly adjacent to the pump, there are no deaths at all, right? Deaths. So kind of think about the argument that he's going to make. His argument in this map. Why are there deaths only around the Broad Street pump? The miasmus theory doesn't really explain that. Okay, doesn't really explain that. The odors were all over the city. Okay, so why would deaths be concentrated right here? So you can sort of see the first part of his argument is kind of challenging the miasmus explanation by providing evidence that kind of contradicts it. He provides some evidence that is difficult to explain using the miasmus theory, but not impossible, as we'll see. Number two, that's not all he does. He also presents evidence showing the absence of deaths in the middle of all that death, the brewery. Why is there a hole in this citywide deaths? Why is there a hole? Well, people at the brewery drank water from their own source. They had a well. They had a well on site. not connected to the Broad Street pump. Well, what was it about the Broad Street pump? We now know the Broad Street pump was contaminated. It was contaminated with water from the Thames. So the map was important, but it wasn't on its own convincing. Johnson writes, Snow could see at a glance that he'd be able to demonstrate that the outbreak was clustered around the pump, yet he knew from experience that that kind of evidence on its own would not satisfy a miasmus. The cluster could just as easily reflect some pocket of poisoned air that had settled over that part of Soho, something emanating from the gully holes or the cesspools, or perhaps even the pump itself. Snow knew that the case would be made in the exceptions from the norm, pockets of life where you could expect death, pockets of death where you would expect life. So what's interesting, when trying to convince someone of something that directly contradicts their own beliefs, it is not uncommon that that person will simply refuse to entertain the evidence that you present to them. They may even, it's possible, oddly enough, it's possible that your evidence could make them believe their original theory more. They may spend more time trying to justify their original belief. I'm sure we've all experienced something like that before. What people did in response to Snow's arguments was to try to find a way to continue to believe in the miasmus theory of disease transmission. So he has this event happen that he thinks is going to really convince some people. He had been at the time reading a lot of work, a lot of publications by the water utility companies, because he was obsessed with water. I mean, that's not exactly right. He wasn't obsessed with water, but he was very interested in the cholera epidemic in London, and he thought that it was being spread through the Thames River, and the Thames River was being distributed. The water from the Thames River was being distributed to the entire city through water companies, the water utility companies. So he was learning about, had become a careful student of the water utility companies. And there was a part of the city that was serviced by two companies, one called Suffolk and Vauxhall Waterworks Company, and the other one called Lambeth Water Company. And they competed over some of the regions south of the Thames River. There were 16 sub-districts with a population of 300,000. And these two companies competed for that market. And Snow writes about the market that was serviced by these two companies. He writes, in many cases, a single house will have a supply different from that on the other side of the street. Each company supplies both rich and poor, large houses and small houses. There is no difference in the condition or occupation of the persons receiving the water of the different companies. So he argues, the competition was so intense that sometimes people on different sides of the street would have different water companies. So in 1849, during the 1849 epidemic, both companies drew their water from the Thames that was polluted with sewage and cholera. London passed legislation that required the utility companies to move their pipes above the city. So let me sort of draw this for you. I don't exactly know how to draw the city, but let's just say that this is London, okay? And here is a house. All right. Here is a house with a person who lives here. All right. And you've got this river, right? You got this river right here. And originally, they got their water from in 1849, they got their water downstream, all right, downstream. Now, but in 1855, right, so they're basically both companies are getting their water in 1849 from downstream of the City of London. So this would be like Suffolk and Vauxhall, and this would be Lambeth, okay, 1849, Suffolk and Vauxhall. And then in 1855, Lambeth moves its pipe but Suffolk and Vauxhall doesn't. Okay, so basically the City of London passes legislation between the two epidemics requiring all water companies to move their pipe inlets, pipes drawing water from the river from downstream, 1849, to upstream, 1855. And Lambeth complies. Suffolk, Vauxhall delay the move. So that in 1855, only one of them had moved the pipe. Jon Snow saw the opportunity to investigate his theory with this move. And he will devise a statistical methodology that we now, to study it, we now call difference and differences method. All right, so let's look at it. So there's two types of data that you see in this book. In the Broad Street picture here, there's individual level data. So he stacks individual level deaths at locations, not for the whole region, right? He's not reporting deaths for the whole region. He's reporting individual level deaths at specific locations. For the Lambeth, Suffolk, Vauxhall section of the book, he's going to report aggregate deaths. All right, he's going to report averages. Okay, collects detailed information from households with cholera deaths and matches it with their utility subscription. So he knows where a person died, whether or not they were a subscriber to Lambeth or Suffolk and Vauxhall. Interestingly enough, just want to say one thing. He does not know if they are drinking from these water companies. He just knows they are subscribers. Okay, so there is a bit of an intent to treat interpretation of his study. Okay. Many residents, though, they didn't know their water company. They weren't the ones that paid it. oftentimes what happened was they paid their landlord a fee for rent that covered all of all their utilities, and the landlord would pay the water company. They didn't know the name of them, and they didn't even know, and the landlord wasn't around for Jon Snow to interview. So what he did though was, because he knew that the water was coming from different parts, the water actually here was saltier, 4 times saltier upstream than it was downstream. So if he tested the water and it was very salty, he knew it was Lambeth. And if it wasn't, he knew it was Suffolk and Vauxhall. Okay, so that's what he does. That's what he does. He does a water test, and he would take samples of the water. He would take samples of the water back to his office and then do a saline test. And then he would mark where the which utility company the water was coming from. He was unbelievably careful and concerned about data quality. Just think about it. Think about this for a second. How often are we as careful as he was? Okay. How often are we as careful as he was? So he does a lot of hard work, which I'll just call shoe leather. Sometimes there's a lot of work that goes into research that is just the hard work of collecting the data. Okay, so sometimes we just download the data from the government. Okay, that's the luxury of 2021. It's so easy to get data, but sometimes we have to build relationships. We have to hand collect data ourselves. And this is not widely appreciated enough. Snow was a model of using both. Okay, he got data from the government, the City of London, on deaths. He hand collected the names of the water utility companies through his own hard work and time. He didn't have a research assistant. Think about it. He was all alone. No one believed him, and he was carefully collecting data. I would like to suggest to you that you make Jon Snow someone you look up to as you go forward in your own research, because of the attributes he possessed when it came to data collection and research. He was honest. He was careful. Honesty in our line of work is oftentimes how we go about handling data sources. Okay. So let me give you a picture of his one of his really key. This is really his main results. All right, these are his main results. It's a table for his diff and diff results. He presents tables. Okay, he presents tables, and here he has Suffolk and Vauxhall, his 1849 death rates. These are deaths per 10,000. Suffolk and Vauxhall had 135 deaths per 10,000 households, and Lambeth had 85. And in 1854, Suffolk and Vauxhall has 147, and Lambeth has 19. Using the difference in differences, he finds 78 fewer deaths per 10,000. What is the interpretation? The move of the pipe upstream above the city caused cholera deaths to fall by 78 deaths per 10,000. That was the, he does not, now, ultimately, Snow only produced in table 12, the second column. The entire table can be reconstructed using multiple tables that he reported, but but his table 12 was actually just this. That's what table 12 was. That's why I call it a modified table 12. But it didn't convince anyone. That's sort of the sad story. Actually, this was the really sad part of it. In spite of what has since been recognized as a classic exercise in data analysis and argument, Snow failed to convince the medical profession, the policymaking establishment, or the public. He didn't convince anyone. And this is the risk. This is the risk of our work. We hope that our work has impact, but a lot of the time, even the best people in our fields may have work that goes unnoticed. We cannot lose heart over failing to convince people, over failing to publish our work as well as we want, or for the work to be cited. Jon Snow's own work went completely unnoticed in his lifetime. And yet it was of utmost importance. It was arguably the most important thing he could have been working on, and is now a classic in health policy, and the social sciences more generally. I think the lesson here is we have to remember which things we can control and which things we cannot control. Cannot control other people and whether they believe us, whether they read our papers, whether they like those papers, and whether they publish them or act upon them. Okay, so you can't. So if we cannot control it, there's a group in the U.S. called Alcoholics Anonymous, AA, and they have a prayer called the Serenity Prayer. And it says, help me to know what I can control, what I cannot control. To change to, so it's important. We have to remember that we can control the work. We can control how we spend our lives and the things that we study and how we study them, what we say about them. But we cannot control whether someone else agrees with us. So to a degree, at some point, we have to emotionally and intellectually let go of the things that are really beyond our own control and focus only on the things we can control. Okay. I know that sounds I don't know what that sounds like, but that's just something I wanted to bring to your attention. Okay. Which was Jon Snow was ignored. His work was ignored. It was ignored by the medical profession, right? His own contemporaries didn't agree with him. It was ignored by the policymaking establishment. The government of London completely ignored him, and it was ignored by the public at large. What's interesting is that in 1866, 8 years after his death, he was vindicated. There was another cholera outbreak in 1866, east of London. And in that outbreak, Snow's ideas were gradually and reluctantly accepted by public officials in the scientific community. 1866 outbreak, why was it so special? It was confined only to the east of London. That was the only part of the city that had the outbreak. And that was the last area that had not yet been connected to the newly constructed sewage system, which discharged sewage below the Thames. The rest of London didn't have an outbreak. And that was the final piece of evidence that swayed skeptics and led to a more reasoned assessment of Jon Snow's data and his analysis. So the things that I like about Jon Snow is I like his long commitment to the topic. The long commitment to the topic led him to reject unsound hypotheses and form new ones based on observation and experience. He showed an expert handling of data analysis, expert handling of the visualization of that data. So his rhetoric, as well as his scientific research, was excellent. So the things to kind of remember about Snow, excellent detective work, excellent analysis, very creative, but also excellent communicator of that information, right? Through pictures, tables, arguments, books. It's just, it's not his fault that people weren't convinced. Let's talk about this this theory or this method, this difference in differences method. Let's look at a simple cross-sectional design. All right. Let's say that all you wanted to do was compare Lambeth with Suffolk and Vauxhall in 1854. And let's just use some notation here. The notation we're going to use is Y will be cholera deaths. Okay. L will be a Lambeth fixed effect, and Suffolk and Vauxhall will be a Suffolk and Vauxhall fixed effect. Fixed effects will be those factors unique to the area that cause mortality, right? They're the unobserved heterogeneity. That's usually what it's sometimes called, the unobserved heterogeneity. All right. Now let's imagine you just compare. Imagine you compare Lambeth with Suffolk and Vauxhall. How will you do it? How will you do this comparison? One way, side by side. Lambeth minus Suffolk and Vauxhall. Call it a first difference. That would be L plus D minus SV. Okay. So we do that. Oh yeah, I forgot one more thing. D, the treatment for moving the pipe upstream. Right, that's the treatment. So we want to know. So we'll D will be the ATT, the average treatment on the treated. All right. Okay, so we're gonna do a simple comparison. What do we get? D plus L minus SV. Notice the form from this comparison? The simple difference in means is equal to the ATT selection bias. This is the same form that we saw on Monday when we decomposed the simple difference in outcomes into causal effects and biases. You see it here. We are reminded that unless L equals SV, this comparison is invalid, right? And the only way that L equals SV is if D is assigned independently of potential outcomes, all right? That's one way we could do it. Another way we could do it is an interrupted time series, all right? So we focus only on Lambeth and we difference over years. 1854, this is wrong, sorry. I keep forgetting to fix this. Okay, so we could say 1854, so do another difference. 1854 minus 1849 for Lambeth. Okay, so then we get L plus D plus T minus L, D plus T. Notice the first difference over time eliminates the unobserved heterogeneity, L. But time introduces its own bias, T, as trends, okay? So this also suffers from bias. We are trying to estimate, we are trying to get an unbiased estimate of ATT, and the interrupted time series will not do it because of the trends. Difference in differences, DID, simply combines the cross-sectional differencing we did with the interrupted time series differencing. So let's do it here. So what we're going to do is, Lambeth, diff 1, L plus T plus D minus L equals T plus D. Suffolk and Vauxhall, diff 1, SV plus T minus SV, T. Okay, so you can see right here, this is the first difference. And then we do the second difference. We go diff 1 Lambeth minus diff 1 Suffolk and Vauxhall. So that becomes T plus D minus T, we get D. The second difference identifies ATT if T is the same for both groups. Okay? If T is the same for both groups. Very, very simple method. But not as simple as we thought. All right? So that's what we're going to talk about today. So let's look at some notation that we're going to use throughout the lecture today. We're going to be talking in terms of sample averages, and we're going to be talking in terms of population expectations. All right. So we're going to use the notation I get from Andrew Goodman Bacon's paper. So this right here, terms delta will be the ATT, the average treatment effect on the treatment group. Oh, sorry. No, I'm sorry. Actually, that's not true. Delta is the DID statistic. Okay. It may or may not be the ATT, but it is the DID statistic. All right. K is a treatment group. U is an untreated group. All right. We're going to call this difference in the first differences. It's called the 2x2 difference. All right. It's the 2x2. That's why I call it right there, the 2x2. Right here. And the post period, post K, is the period of time after group K was treated. Pre-K is the period of time before group K was treated. All right. So we define treatment dates. We defined the treatment dates pre and post with respect to group K, not group U. U is never treated. U is not treated. So there is no post U treatment. There is only post group K treatment. All right. Only that. Now we're going to go from samples to population expectation. So look, notice the difference here. All right. Now we're working with the universe, not working with the sample anymore. We're working with populations. And what we get is expectation outcomes for group K in the post period, in the pre period, expectation group U for its outcome in the post and the pre. Now, what I'm going to do is, all right, let me anticipate. Let me show you what I'm about to do. All right. I'm about to go from this equation to this equation. There's an intermediate step, though. First thing I'm going to do is, before I go to the next slide, I'm going to change each value of Y with its potential outcomes. So if in that period, that group is treated, I will replace Y with Y1. If in that period, that group is untreated, I will replace Y equal Y0. All right. So let's look at this right here. Post period. Well, in the post period, group K is treated. So I'm going to give that a Y1. And in the pre period, it's untreated. So I'm going to give it a Y0. And this is always untreated. All right. So I can rewrite this entire expression as expectation Y1 for group K in the post minus expectation Y0 group K in the pre. All right. So all I've done is just use, this is just introducing potential outcomes notation into our 2x2. And the reason we introduce potential outcomes notation is that potential outcomes notation is how we express causality and bias. All right. And having having a notation in terms of having a notation like potential outcomes will guide us into assumptions needed for identification, as well as the design of estimators that can reliably, which means statistically, delete those bias terms. All right. And what I'm going to do is I'm going to add a 0 to this expression to the right-hand side. So I'm going to add in a 0. My 0 will be expectation Y0 K post minus, expectation Y0 K post. All right. That equals 0. I'm going to add it. I'm gonna add it, oops, to the right-hand side. All right, let's add in the 0. There's the rewriting of the equation. Then I'm going to add in a 0. And I'm going to rearrange. All I've done here, I just rearranged the previous slide to illustrate causality and bias. Here's the causality. Here's the causal parameter we care about, the ATT. Notice what the ATT is. All right. It is expectation Y1 for group K in the post period, expectation Y0 group K in the post period. So notice the causal parameter, ATT, is counterfactual based. We don't observe Y0 group K in the post period. All right. By definition, we don't observe that because in the post period, by definition, group K was treated, not untreated. So that's an untreated state of the world. All right. It's an untreated state of the world. Then we get this. What is this right here? This is simply what's left over after we rearrange the expression. And so what we see is this is a trend. This is a trend in group K's Y0 term. And this is a trend in group U's Y0 term. All right. And if these two groups had the same trend, then the 2 by 2 will amazingly enough equal the ATT. Jon Snow may not have known it, but he actually was assuming parallel trends, right? That's what this is called right here. This right here is called parallel trends. Parallel trends simply means that the above blue terms are equal to each other, or that the difference is 0, right? And it's a parallel trends is not a randomization assumption like independence, right? It's not a randomization assumption like independence. Parallel trends is a restriction assumption. We are restricting parametrically the flow of potential outcome Y0 over time for these two groups. And it is not testable because we can't observe Y0 group K in the post. And so since we can't observe Y0 group K in the post, we can't evaluate whether or not that trend that would have happened is equal to the trend that did happen. All right. So there's another famous diff and diff study that happens much later. So Jon Snow's work was the 1840s or 1850s. And there is another study that happens in labor economics. Well, actually, so what I should say is that there is a long stretch of time where the difference in differences method is really never used again in any of the social sciences. There's traces of it every now and then, but for the most part, it wasn't used. Definitely didn't have a name, but it wasn't until, but then in the 1970s, in the United States, there was a Princeton economist named Orley Ashenfelter. He's still alive. Ironically, I just actually wrote him about an hour ago, asking him if I could interview him. He is a distinguished professor in the economics department at Princeton, labor economist. He was the advisor for David Card and Josh Angrist. So he's had a massive influence over the direction of causal inference methodologies in the late 20th century. And he was using difference in differences methods. He was using difference in differences methods to study job trainings programs, retraining of workers, and seeing if it improved their wages. That study, that method was then used by David Card and Alan Kruger in a classic study of the minimum wage. All right. Now, I'm not going to go through this minimum wage study. The thing I want to actually illustrate here, though, is that it's very common. All right. There's basically, several ways. There's a few ways you can calculate the 2x2. You can use the sample averages. You just need 4 data points, right? You need 1, 2, 3, 4, right? You can just use the sample averages, or 2, you can use OLS. But if you use OLS, what's the model specification that will isolate the ATT? Right? So there's many reasons. I call it two-way fixed effects here. So let me just write that out. What's commonly done, as we'll see, is that the OLS specification will oftentimes be the panel fixed effects estimator, which is OLS with time dummies and group dummies. Okay, two-way fixed effects. All right, two-way fixed effects. And there's several reasons to use two-way fixed effects. First of all, it can isolate the ATT. All right, it's easy to calculate the standard errors. You can adjust for heteroscedasticity really easily. It's easy to include multiple time periods. You can even include treatments with different treatment intensity. But there are also bad reasons to use two-way fixed effects, which I'm going to discuss really for the rest of the day. Now, here is the specification in the 2 case. So this is the 2-group specification of the OLS model, right? In a DID design. You got your outcome, alpha, gamma, dummy. So this was for, so we're going to have here NJ, treatment group, D, DT, post-treatment period, and Y is the outcome. All right, alpha is a constant. All right, so that's all that it is. New Jersey, this is called New Jersey. NJ is the treatment group. DT is a post-treatment period. Y is the outcome. Alpha is a constant. Our data is collected in 2 periods: before, pre, and after, post. All right. Okay, so we're going to estimate this regression. All right, but let's just imagine first, before we estimate the regression, why does this specification identify the delta, the same delta in the 2x2? Why does this specification identify the same delta in the 2x2? Okay, well, look, let's go through the mechanics of that simple 2 by 2 before. Okay, so let's go through the 2 by 2. So let's do the first difference. All right. So this would be post minus pre. So this would be A plus lambda. Oops. Minus A equal lambda. All right. Do the same thing again here. So we go post minus pre, and that's A plus gamma plus lambda plus delta minus A plus gamma. That gives us lambda plus delta. All right. So when we go through all these differences, what happens is we delete this one, we delete this one, we delete this one, we delete this one. All right. And then when we do this difference, it's New Jersey minus Pennsylvania minus this other state, this other area here. This is the untreated group. So then it becomes L plus D minus L equals D, right? So if we do the 2 by 2, then we will have isolated the delta parameter. And if we run this regression, the coefficient on the interaction is the same coefficient as the 2 by 2. So that's what I want you to notice. The coefficient on the interaction, D, delta, is the same value as if we had calculated the 2 by 2 manually. All right. This is without, but this is only true without covariates. All right. This is only true without covariates. All right. So let's look at this. What exactly is being calculated when you run this regression? This is the untreated group here. So this is the untreated group in black, and this is the treated group in red. All right, it's untreated group in black, and this is the treated group in red. And the value here, alpha, is the value, alpha, this distance right here, alpha, is the value of the outcome in the pre-period for the control group. The gamma part is the difference between the treatment group and the control group in the pre-period. The lambda part is the change over time for the control group. So then what's delta visually? Delta is the change in the outcome between the above red dot and the below black dot. But what is the below black dot? The below black dot all right, so that right there is the trend. That right there is the trend in the control group. And that is the trend. That right there, the below thick red line, is the parallel trend that would have happened in the treatment group had the treatment group never received the treatment. OLS uses the control group trend to plot out a counterfactual. And then using that trend identifies delta as the difference in the outcome post-treatment to what is projected to would have occurred using the same trend from the control group. Okay. OLS always does this, regardless of whether parallel trends is true. Okay. Always does this. It always uses this trend to project a counterfactual. But see, this delta right here is only the actual causal effect if that line right there is what would have happened in the control group had the treatment never happened. So if parallel trends doesn't hold, then the ATT won't be identified. But regardless of whether parallel trends holds, OLS always estimates the same thing. It always, if this is right here, if this is right here, the trend, okay, this is the trend right here, OLS will always, it'll always identify this distance right here. Oops. Okay. So let's imagine, let me see something real quick. I've always wondered this. I feel like I've been doing this wrong. So let's see. Neither one of them is right. Could have sworn that I drew this right. Should be drawn like this. Okay. So this right here is what this right here is what OLS will identify. All right, OLS will identify that, okay, using that trend. But let's say, so this is the control group trend. That's the control group trend. And this right here is the true counterfactual trend, right? This is the true counterfactual trend right here, right? Doesn't matter. Doesn't matter that that's the true counterfactual trend. If this right here, is what the, if this right here is the trend that happens in the control group, OLS will always estimate that amount right there, even if the true effect is this down at the bottom. All right. So regardless of whether parallel trends is true, OLS will always estimate the gap between observed treatment, post-treatment period, and projected values off the control group trend. Okay, which is to say, this. All right, I gotta fix this picture. Okay, so it is 30 minutes, it's 25 minutes on the hour. Let's take a 10-minute break and we'll come back in 10 minutes. All right, we'll come back in 10 minutes. So let's take a short break. Or let's, if you can hold off that question for a little bit, it'll be the the major drawback of two-way fixed effects is more complicated than that. It actually isn't. It's actually not a problem at the moment. Everything that we just showed shows that, you know, two-way fixed effects works fine in the two-group case. It just needs parallel trends. And that's not really a weakness of the two-way fixed effects estimator. The difference in differences design, the difference in differences design is a design. It's a class of approaches that require parallel trends. So no matter what method you're using to estimate causal effects and a difference in differences, the definition of a differences in differences design is that parallel trends assumption. All of the difference in differences estimators depend upon parallel trends in some way or another. The weakness of two-way fixed effects is how it handles heterogeneity. That's the main thing, which hopefully I can do a good job explaining. So the identifying assumption for all diff and diff designs is parallel trends. And parallel trends cannot be directly verified at all because technically one of the parallel trends is an unobserved counterfactual, but one often will check for parallel trends using pre-trends. All right. So technically, let's look back at this. All right. There are no pre-trends. Notice here, there are no pre-trends in this picture, right? There is only before and after. Pre-trends are the periods prior to the first period, though. Okay, they are the before periods. All right, and we don't technically need anything to be true about pre-trends in order to estimate the ATT. All we need in a two-group, two-period situation is that the counterfactual trend for the treatment group equal that of the untreated group. All right, that's all we need. But since that cannot be tested, people will usually test the pre-trends to see if those are parallel. That's a standard, okay? In the same way that the McCrary density test is standard and obligatory in RDD, event studies are standard and obligatory in diff and diff. Okay, they're standard methods. Right, and this is what that looks like. This is what that looks like. So what you can do, what is often done, this is called the event study. Now this is different. This is not the same event studies that you may have learned in a finance class. All right, this is the diff and diff event study. All right, all you're really focused on is two things. Are the trends in the pre-treatment period, are the trends in the pre-treatment period the same for the two groups? Notice I said trends, not levels, right? You can see here that the levels are different, right? The levels are different. This one's higher, okay? So the levels are different. Black group has higher levels than the red group, but the trends are the same, right? And it's ultimately, and because the identifying assumption for DID is parallel trends, because the identifying assumption for DID is parallel trends, event study plots tend to only focus on the pre-trends, not pre-levels. Okay, pre-trends, not pre-levels. That said, when pre-levels are very different from one another, Kahn, Lang, and Lang, 2017, I think, argue you should have a good understanding as to why they are different, as to why levels are different. But ultimately, regardless, pre-trends are not necessary for estimating causal effects. They are simply a kind of indirect evidence for it. All right. So you see right here. So here is, in this right here, the we plotted. We said, because we had two groups, because we had a 2x2 situation, we simply plotted the raw data. Right? Because we had a 2x2 situation, we simply plotted the raw data. So are the trends in the pre-treatment period the same? And two, what are the dynamics of the in the post-treatment period? So people use event studies to provide evidence for parallel trends, as well as to estimate dynamic treatment effects. Right? It's the two reasons that they do it. And here is an alternative. So, so there's two ways to do the event study: plot the raw data, plot regression coefficients. Okay, plot the raw data, plot regression coefficients from a fully dynamic model. Right, and this is the traditional event study specification. Okay, this is the traditional event study specification. You've got the fixed effects here. All right, you've got these fixed effects for group and time. Then you've got sequence of dummies. These are called leads on the treatment. Then you've got lags on the treatment. And historically, maybe somebody would put some covariates in. They might put covariates in. All right. This is really the common way that it was done historically. And then what would be done is you would estimate this equation, and you would graphically plot the gamma and delta terms on to visualize. You would graphically plot it with point estimates and 95% confidence intervals on a simple graph. All right, so let me give you an example of a really good paper by Sarah Miller, Laura Wary, and I apologize, I've forgotten the third author's name. They studied a program in the United States called Medicaid. Medicaid is our healthcare program, universal healthcare coverage for lower income families. And they examined a rollout of Medicaid under President Obama's massive healthcare program, the Affordable Care Act. And the Affordable Care Act or what's sometimes called Obamacare. The Affordable Care Act, what it did was it provided subsidies for states to expand their provision, to be more generous, to provide more healthcare coverage for slightly wealthier families, all right, but still low income. What they did was they linked that large scale survey data with administrative death records, and they estimated that Medicaid caused a 9.3 reduction in annual mortality. And they argued that it was driven by a reduction in disease-related deaths. So let me show you the event studies that they did. All right. So what they did was they estimated that equation on Medicaid eligibility. They have to drop one of the dummies. So, you know, you've got this fully dynamic model, but you can't put in everything. All right. You can't put in every dummy. You're going to have to drop at least one. So usually people will drop -1, the one just prior to treatment. All right. So that's where you see right there, they drop -1. They plot the coefficients. So these are beta coefficients in our OLS regression. These are 95% confidence intervals. And you can see right here that after Obamacare, or sorry, the Affordable Care Act expanded, on average, state Medicaid eligibility in the treatment states grew by about 40 percentage points. All right, so more people become eligible, more people end up being covered, and there's a significant drop in the uninsured population. So in some ways, this is an interesting paper. Again, this is an interesting paper for the rhetoric. Okay, this is not a study about uninsured or coverage. It's about mortality. But these authors first make a layered argument that the program had an impact on the population enrolled on the population being insured. All right, that's the main thing I want to kind of point out here, is that notice the rhetoric. They are going to first convince you that the Affordable Care Act changed the number of people insured, all right, who went from uninsured to insured. Okay, they'll do that before they present their main results. All right, they're going to do that before they present their main results. And here's their main results. All right, here's their main results. They basically are finding, you know, before the treatment occurred, and it's not a, you know, this picture is not nearly as good as that picture, but you've got somewhat larger confidence intervals. You've got point estimates that are close to 0, except for this one, which is slightly above 0. And then it falls. Okay. So many papers will, when they are estimating their standard errors, so this is a good example. Basically what I'm saying is that this is a good example of event studies. So you have here the plotting of raw data and the plotting of regression coefficients. Usually people do this one. Now, many papers will use difference in different strategies using data from many years, not just one pre and post period. They'll do many different periods. And when they're using many different periods in an OLS regression, and they have aggregate data, the outcome variables are often serially correlated. So one of the main, okay, I got a question. When we take the logarithm of the dependent variable to conduct diff and def, should we show the log value or the raw data to check the pre-trend? You should show whatever it is that is going to be your specification. Really, what you should do for when making choices about things like like logs, you want to choose a specification that gives you the most confidence in parallel trends. So if logging gives you better pre-trends, then you will be arguing for parallel trends in logs, and you will present analysis in logs, because logs are the only ones you can justify. What are the values on the horizontal line? All right, let me go back. Angelica's asked, what's the values on the horizontal line? This is time. This is the dt plus 1. So what this is each dummy is a dummy for a group at a period in time. So let's say the panel is 10 years and the treatment occurs in 2005, right? In the event study, you'll have a dummy for treatment times 2001, treatment times 2002, treatment times 2003, treatment times 2005. You'll skip 2004 because it's the t-1 baseline, and so forth. Okay, so this is going to be what this is going to be here is this will be the t-6, t-5, t-4, t-3, t-2. That's the t-1. So here on this side, on the left side of the dashed vertical line, we are assessing the plausibility of parallel trends by studying pre-trends. And on the right side of the dashed line, we are estimating dynamic treatment effects, right? This is only for the simple 2x2 case for now. We will discuss later more complex designs, but for now, there is only one treatment group, and one treatment period, and one untreated group. All right. Okay. All right. So standard errors. Okay. Historically, if you think about this period in economics where potential outcomes and counterfactuals began dominating our theories of causality, then there's an early diff and diff period and a later diff and diff period. Okay. In the early diff and diff period, always used two-way fixed effects, always used multiple periods, and they always corrected for heteroscedasticity, not clustering. One of the few diff and diff theory papers in that early period was by Bertrand, Duflo, and Mullenthan, 2004. Should we trust difference in differences? This paper was only focused on inference, standard errors, variance of the estimators. Okay, That's all it was focused on. It was not focused on unbiasedness. It took for granted that the DID first generation papers were unbiased under parallel trends. Okay. It took that for granted that it was unbiased under parallel trends. The question was with regards to the bias of standard errors. Okay, with regards to the bias of standard errors. And what they pointed out is that because of this serial correlation in the aggregate outcomes in the panel, the conventional standard errors often severely understated the standard deviation of the estimators. Standard errors were biased downward. Now, they weren't the first ones. They were not the first ones for reasons I do not fully understand. Bertrand, Dulo, and Mullenthan are not the first to suggest what I'm about to suggest the solutions I'm about to say, but this is the paper people routinely remember. It was actually earlier work by Moulton that said many of the same things. Okay. You're welcome, Angelica. So if you've got these severely biased standard errors, too small standard errors, and you're over rejecting too often, then what can you do? And they went through a lot of different solutions. They had many different things that they considered. And there were three solutions that were theoretically attractive and that did well in the Monte Carlo simulations. They were bootstrapping, there was clustering, and then there was this strange one called aggregating the data. All right. So block bootstrapping was the one solution. If you analyze, if you consider the states to be blocks, then what you could do is just simply, run your diff and diff, and then just, sample with replacement the data, run your diff and diff on those subsamples, get some distribution of coefficients, and use the standard deviation of that distribution to get a standard error. That's one thing you could do. I've actually only seen one person ever do that. What's much more common is to cluster standard errors at the group level. Now, the reason why I think that got adopted, or one of the reasons, that there could have been theoretically attractive reasons, but one of the reasons was it was really simple to do. It didn't require a lot of programming skill. But bootstrapping requires a little bit of programming. Sometimes you have more. There's so many different kinds of bootstraps, and you might have to put in some programming, put in some loops, storing the estimates. Trying to do some calculations. Not everybody has that skill, but everyone can type in cluster, cluster, right? Everybody can do that. So that's typically what people do. That's also what you should do as well. But this other one was kind of strange. It was called this aggregation method, this residual aggregation method. What they recommended doing was aggregating the data into one pre and post period, and just running the regression off the pre and post dummy. But that only worked if you had one treatment date. So if you had staggered treatment dates, what they recommended was regressing the outcome onto fixed effects, get residuals from the treatment states, and then divide them into two groups, pre and post. Then regress the two groups of residuals onto a post dummy. I've literally never seen anybody do that one. So it's very common for readers and others to request a variety of robustness checks from a diff and diff design. So one is the event study, and another is a falsification test using an alternative control group. And this is called the triple difference. And then another one is to use a placebo outcome that is not treated. So these two right here, these two are other forms of placebos that one typically might do in a conventional DID, all right? In a conventional DID. So this is the triple difference, all right? So let's look at the triple difference. Let's say that we had a minimum wage study, and the minimum wage is happening in a state called New Jersey, but it is not happening in a state called Pennsylvania, all right? It's not happening in a state called Pennsylvania. And the minimum wage should only affect low wage work, should not have any effect on high wage work, all right? You got to observe the low wage workers after and before. You observe the high wage workers after and before, and you do it also for the control group, okay? Now look what we're going to put in here. For the low wage worker in the after period, you're going to have a fixed effect. You're going to have a global time trend. You're going to have a treatment group trend, and you're going to have a group trend. So this is called a group, all right? Notice I call it a group right there. You're going to have a group trend. And then you're going to have the treatment, the minimum wage itself. So after you've got these five terms. Before you just have one. But in everywhere else, the after is just 4 terms, right? So it's 4, 4, 4. But in the, in the treatment group, it's 5 because you've got that extra treatment effect. So we do the first difference, right? So when we do the first difference, we're going to delete all of the fixed effects. So anytime you do the before and after, you delete the fixed effect. The unobserved heterogeneity is always deleted. Time invariant unobserved heterogeneity is always deleted when you do those before and after differences. Okay. Now we're going to do a difference between the two groups. Okay. We're going to do a second difference on the two groups, and that's going to delete this. Right. So look real close. It's going to delete that. It's going to delete that because that's the same for the two groups. It's going to delete this. It's going to delete that. All right. And then we're going to do another difference. Now this time, when we do this difference, look what we get. We get, when we did that second difference, notice what we get. We get this and we get this. All right. So we're going to do one more difference between the two groups. This is a diff and diff right here, and it's biased. It's biased. So we're going to do this difference. And when we do this difference, this and this disappear. All right. So what do we need to be true? What is the identifying assumption needed for diff and diff? T is the same for all groups. State trends are the same within, or actually, I'll just stick to the main one. Main identifying assumption is, notice it's right here. Here, there it is right there. Okay, so, oops. So the main identifying assumption for triple diff is that the gap, the dynamic gap between the dynamic trends, the gap in the dynamic trends between groups is the same for the treatment group, for the treatment state, and the control state. That's all we need. We need for the difference between the low income, the low wage worker, and the high wage worker to be the same for the two groups. it's a version. It's a version of parallel trends, but it's a parallel trend for the subgroups, not the experimental groups. Okay. This method, this triple difference, goes back to a paper by John Gruber at MIT. Right. And here was his study. There was a study done where they were evaluating the impact of a state mandate that required states to cover maternity leave for pregnant mothers. And he evaluates this by looking at the experimental states and the non-experimental states. And he's got a group of people that are likely to be affected, which are married women of childbearing age. And then he's got a group, he's got it for the experimental states and the non-experimental states. And then he's got a control group. And this is going to be groups of people. This is going to be groups of people who are not affected by the law. This is older women. And this is single men ages 20 to 40. All right. Single men ages 20 to 40. Neither of these people are believed to have been affected by the law. Right. So they're going to do difference. Then they're going to difference the difference here. So you're going to go, here's how the method works. You're going to go difference. Right. So this is 1.5 minus 1.54. You get a negative 0.034. All right. So then you go 1.397 minus 1.369. That's a slightly positive number. Then you difference that. You go negative 0.034 minus 0.028. That gives you negative 0.062. Now what this is the diff and diff parameter for the 2x2 case. The triple diff will do the exact same analysis, but for the subgroup males and older females not believed to be affected by the treatment, but which are affected by the unobserved heterogeneity. Okay. So we'll go through again. We'll do the whole thing again. Difference. Right. So then right there, we get a DID parameter for the 2x2 case on our placebo. Notice here it is 0, right? Negative 0.008, right? Negative 0.008. Then all that we do, the triple difference, simply differences negative 0.062 minus negative 0.08, which is negative 0.054. Okay. Now this is this is using sample averages. All right. This is using sample averages. But we know from earlier, you can estimate DID using OLS. You can also estimate DID using OLS. But the structuring of the data is more layered, and the model specification is a little more involved. Okay, it's a little more involved. So let's look at it. All right. So I'm just going to put in here how the data is structured. So what you're doing, remember what you have. Remember how your data is structured. Data structure is. You've got states. You've got groups. You've got years. So your triple diff will be an interaction of all three. All right, it's going to be an interaction of all three. So here's what we're going to get. This is a post dummy. So that's this one. This is a group dummy. So that's this one. And this is a state dummy, which is this one, right? So these are just the dummies by themselves, all right? And then what we're going to do is we're going to interact them, all right? So here is the delta for the group interacted with time. Here is time interacted with state. Here's state interacted with group. And then you have the full interaction. And in the OLS specification, okay, beta 8 coefficient on all three interactions is our parameter. And it will identify the ATT under that version of parallel trends I showed earlier. Okay, that will equal the ATT under that assumption that I did earlier. I'm going to skip this discussion of an old paper of mine so that I can get to these new estimators. All right. So everything that I did so far, let's review real quick. 2 by 2, 1 treatment group, 1 treatment period, no covariates. All right. So it was OLS for a 2 by 2, no covariates. All right. What about covariates? How will we control for covariates? Turns out it is not as straightforward in a DID as we thought. All right. So part of the new literature on difference and differences has been the focus on covariates. That's been a couple of key papers, or about 3 key papers. Shun said, so triple diff is for checking whether there is unobserved heterogeneity that cannot be controlled by fixed effects in DID. Exactly. That's exactly right, Shun. That's exactly why you do it. It's if you believe that you've got additional levels of dynamic unobserved heterogeneity that you can't control for in that fixed effect specification. And triple diff is just a way of trying to find control groups to delete that dynamic unobserved heterogeneity, like the trends that are happening in a treatment state over time that'll contaminate your double diff. We'll just find a set of units that are also being treated with those trends. That's the basic idea. It's a really simple idea. It's basically what triple diff is doing. Triple diff is just staying committed to that diff and diff framework, just finding an additional control group. Okay, it's a version of placebo kind of analysis. So that's exactly right. Very good. All right, so let's look at some models that are focused on covariates. It was very common. Anybody on this call that has run a diff and diff model, including myself, has often included covariates in the specification, because that's the thing about OLS. When you think about what OLS does, what does OLS do? Y equal A plus DD plus BX plus E. It is trivial to include covariates in a multivariate linear regression model, right? It's not that is historically one of the strengths of the mechanics of OLS, the inclusion of additional variables, so that the inclusion of additional variables, right? But what we will show is that in the DID, including covariates actually causes us to add in more assumptions than merely parallel trends, right? So let's get into that. So we're going to discuss two papers, Alberto Abadie's 2005 semi-parametric diff and diff paper, and a Journal of Econometrics paper by Santana and Zhao in 2020. And in some ways, you can think of the Alberto Abadie paper as like a parent to some of the papers that we're going to discuss in the contemporary diff and diff literature, because of its representation of how to handle covariates. Right, so there's a paper that we're going to discuss here under differential timing called Callaway and Santana, and Callaway and Santana will be based on that Alberto Abadie paper, as well as this Santana and Zhao paper. All right, so the Abadie paper is really best used for longitudinal data or repeated cross sections where treatment occurs at one point in time. But like Callaway and Santana, it's used for modeling the differential selection based on what you think are covariates, which means you need to be careful about, you need to think carefully about what those covariates need to be. So it's a short paper. It's very readable. Alberto Abadie is a very, he's one of the best econometricians alive. And it's, even when it gets into theorems and proofs, it's still short and readable. It's a very deep, subtle paper. And I think a way to think about the paper is this quote by Daniel McFadden. A good way to do econometrics is to look for good natural experiments and use statistical methods that can tidy up the confounding factors that nature has not controlled for us. That's a way to think about diff and diff. Look for natural experiments, use statistical models to adjust for confounders. That's really what this all is about. So when would you use this? Well, you use it when you don't have randomization. And remember, diff and diff doesn't require randomization. When we were working through that early potential outcomes notation, we showed that one of the things that, we could use to isolate an average treatment effect was independence, but diff and diff never uses independence. It never uses randomization. It uses restrictions on parallel trends. So you'll use it when you're willing to make those kinds of restrictions on unobserved counterfactuals, and sometimes the selection into treatment will only be based on observable covariates. All right. So Abadie is going to propose a method that will estimate the average treatment on the treated. It is a diff and diff type estimator, but it is not two-way fixed effects. All right. So it is an alternative to OLS. You're going to need a treatment group and a comparison group before and after. And you're also going to need a new assumption. You are not going to be using the parallel trends assumption. You are going to be using what is called the conditional parallel trends assumption based on X. So why do we do this? Well, sometimes we need to control for things, right? How often is it that you'll run a diff and diff and you'll include controls? Why are you doing that? You're basically assuming that you need these controls to adjust for unobserved confounders. Well, another way to say that is to say that the treatment assignment is based on covariates. All right. And so what you're going to do here is you're going to be essentially building a model based off the principles that you need to control for covariates in order to satisfy parallel trends. So he's not going to be proposing an OLS model with fixed effects. Abadier is going to be proposing a much simpler difference in means in a DD framework using a specific form of weight called the propensity score, which will have been estimated with a polynomial logit or a polynomial series using linear probability model or logit. So this paper is not a critique of two-way fixed effects. All right. Andrew Goodman-Bacon, that we will discuss momentarily, that is a critique of two-way fixed effects. Andrew Goodman-Bacon is not going to propose an alternative to two-way fixed effects. Callaway and Santana, that I'll discuss momentarily, that will be an alternative to two-way fixed effects. Abadier is an alternative to two-way fixed effects. That's the way that you want to think about this new literature. So the way that I organize, part of the way that I organize this new DID literature is it a critique of two-way fixed effects? Abadier is not. Does it develop an alternative to two-way fixed effects? Abadier does this. All right. So some papers like this one here, Andrew Goodman-Bacon is. Andrew Goodman-Bacon does not. All right. So in this new DID literature, there are some papers that are critiques of two-way fixed effects, and there are some papers that are presenting alternative estimators. Right. Andrew Goodman-Bacon is a critique, but not an estimator. Abadier is not a critique, it is an estimator. And some papers are both. Right. So that's one thing to kind of keep in mind as you're working your way through these papers is sometimes they're critiques of two-way fixed effects, and sometimes they are developing new tools. All right. And sometimes they do both. It's just how these people are writing these papers. So here is the three-step method for the Abadier estimator. What you're going to do is you're going to compute each unit's first difference. So that's going to be the after minus the before. That's the diff and diff part. Most of these, though not all, most of the DID estimators are based on simple difference in means using before and after, right? And Abadier is like that. It will calculate a before and after mean, difference in mean. It will then weight that first difference using the propensity score, all right? So then you're going to compute that before and after. You're going to estimate a propensity score. You're going to weight the before and after using the propensity score. Inference will take into account step 2. And what's nice is you can have heterogeneous treatment effects and it not be a problem. All right, so T is going to be the year of treatment. We're only going to have 2 groups. The treatment will not vary across units, so there won't be any kind of staggered rollout or differential timing. Our notation is going to be potential outcomes, Y1 and Y0. D is going to take on a value of 1 or 0 based on group and time. So that's a dummy based on whether a unit is treated. B is going to be the baseline period. And X is going to be baseline covariates only. So we will control for covariates, but only in the modeling of the selection into treatment. And since we are modeling the selection into treatment based on covariates, we only use the baseline values of the covariates. for that modeling step. Okay, we're only going to do it for that. So what are the assumptions that we're going to use? Parallel trends assumption. I'm going to say it again. DID is a class of estimators, just like IV is a class of estimators. And what is common for all these estimators in DID is the parallel trends assumption. That's what unites all DID-based estimators. Okay, so that part is not a two-way fixed effects. It isn't just two-way fixed effects that has that PT assumption. Body A is not two-way fixed effects, and he has a parallel trends assumption, right? But it's conditional. It's a conditional assumption, right? So here we have conditional parallel trends. What does that look like? That says that in a world without treatment, the trend over time, so this is T post-treatment, this is B baseline, all right? So the treatment occurs between these two periods. We look at the trend in potential outcomes in a world without treatment for the treatment group and for the control group. But we're going to require parallel trends to hold within values of X, okay? And then because we're going to be using these covariates, we're going to have this additional assumption called common support. And common support just means that every value of X, all right, there is a treatment group and a control group, right? So what that's going to mean is for males, there are groups of males in the treatment and groups of females in the, there are groups of males in the treatment and groups of males in the control. Common support just means that across all values of X, we have both treatment and control units. Now we're going to express that common support though, because this paper is going to use covariates. It's going to use, propensity scores. We're going to express common support in terms of the propensity scores. Okay, so we're going to need it for the propensity scores. Here's a picture of common support. Here's a picture of common support. So this is going to be the distribution of the propensity score. The propensity score, for those that don't know, the propensity scores are useful for a few reasons. One, if you have many covariates, then you may have too many covariates to satisfy common support. That's called sparseness. Propensity scores will absorb, for lack of a better word, all of the information in those covariates and collapse them into a single variable, as opposed to tens or as opposed to dozens or hundreds of covariates. So part of the reason we like propensity scores is they reduce the dimensionality of X into one dimension, the propensity score, right? Two, once we have the propensity score theorem by Rosenbaum and Rubin, I think it's like 1983 or something like that. The propensity score theorem states we no longer even need those X covariates. The propensity score has all the information we need. Okay. So what we're going to do is we're going to evaluate common support, not in terms of the covariates, but in terms of the propensity score. And so you've got this propensity score. The interpretation of the propensity score is conditional probability of treatment. So if you are a male, what share of the population is in the treatment group? So if there's 100 males, 75 are in the treatment group, we say the propensity score for males is 0.75. It's the conditional probability of treatment. Conditional on being a male, what is the probability of being in the treatment group? It's a frequentist definition, not a Bayesian one. All right, it's frequentist one, not a Bayesian one. All right, so we've got this distribution here of the propensity score. I'll usually use p hat. And here's the treatment group propensity score, and here's the control group propensity score. And what we need, so notice what these guys are right here. Okay, so I've got that. All right, so the green shaded area is the common support region. This is the part of our experiment where for every value of the or for the distribution of the propensity score, we have units in treatment and control, right? The red shaded region is the non-support regions, right? In the one on the left, that is D = 0 control group. We have units in the control group for those propensity scores. No one in the treatment group. For the red shaded region on the right, D = 1. We have units in the treatment group with those propensity score values, but no one in the control group, right? So common support is referring to the green zone. And sometimes what people do is drop the red region using either min and max values or some rule. Crum et al. Suggests dropping all units with propensity scores less than 0.1 and more than 0.9. Propensity scores, since they are probabilities, must be between 0 and 1. All right. So first thing we're going to do is we're going to define. So I need to change these slides just because I used to teach it in this particular order. So we're going to define the parameter of interest as the ATT. And that is going to be the difference in between Y1 and Y0 at a given point in time for the treatment group, right? A Baudier's estimator will give a consistent and unbiased estimate of this parameter, right? So this is the parameter of interest. And this will identify, a Baudier's estimator will identify ATT under conditional parallel trends and common support. Okay. Now here's how it's going to work. You're going to calculate before every unit. Remember the steps. Calculate before and after per unit. Okay, so that's that right there. 2, calculate the propensity score per unit. 3, weight the before and after with the propensity score, right? So let's look at the propensity score. There it is. Okay, so that's the propensity score. We're going to estimate that with data. That's the true propensity score. We're going to estimate it with sample averages. And so if you are in the treatment group, okay, you'll what you'll get in the treatment group, okay, is that'll be a 1. And if that's a 1, then this will be 1 minus the propensity score divided by 1 minus the propensity score, which means that'll cancel out. And so for treatment groups are only weighted by that denominator. And that denominator is basically an average. It's basically an average. It's the share of the population in the treatment group. So it's just dividing by the number of units in the treatment group, right? So it's only going to be weighted by that denominator. But control group units will be weighted by the propensity score, which will weight up those units who have very high propensity scores. Okay, so look, when you have a 0, if you're in the control group, and that goes away, and then your weight on this before and after is the negative. It's basically like a the weight is an odds ratio version of the propensity score. You can see it right here. So it's basically propensity score fraction divided by 1 minus the fraction. And the negative here is what's going to indicate this part. Okay, so this is basically how you're kind of imputing those counterfactuals. You're going to do that for every unit, then you're just going to average over all of them, right? There's almost no guidance I've usually seen when you're to estimate the propensity score. Now there'll be guidance over what units to use for estimating that propensity score, but there won't be guidance oftentimes as to like what the proper specification is. It used to be that like in DESI and WABA, there was an effort to estimate propensity scores in order to achieve balance on covariates. But you don't usually see as much on that I've seen. I mean, I'm not a huge reader of the propensity score literature, but oftentimes I haven't seen a lot of guidance. So Abadier is different. He is going to give guidance. And the guidance he's going to give is to estimate a series of polynomials based on those X controls. That's what he's going to, so the name of the paper is semi-parametric diff and diff. The semi-parametric part is because of this polynomial specification of the logits. So you're going to either estimate it with OLS. You're either going to estimate it with OLS, which I hadn't actually ever seen before. Usually I've seen people use logit and probit, but he's going to allow for OLS linear probability models, or he's going to estimate something called a series logit. Right? It's going to do one or the other. So it's common to hear people say we don't know the propensity score. We can only estimate it. So you don't actually know the true propensity score. And that means you don't know fully the treatment assignment. You might not know that the covariates that you need to be controlling for. Same here. We're going to approximate it. So here's the OLS model. Estimate the probability of treatment based on X's. You're going to put in these covariates here in terms of their polynomials, or you're going to put in your covariates for the logit. The stata command to do it is called absdid, and you just need a variable indicating if you're in the treatment group or the control group. You need X variables, which can be a list, the order in which the variables occur, and you need the exact estimator. So why not? So you can do it yourself. You can download this data. You can estimate it yourself. When do you use this, though? When do you use the Abadier estimator? You use it when you have a baseline period and a follow-up period, and you have longitudinal panel data. You can use it with repeated cross sections, but usually probably, well, you can use it with repeated cross sections too, but it's very commonly, probably more commonly used with panel data. So that's the Abadier paper. Let's take a, so that was another hour and 15 minutes. Let's take a 10-minute break real quick. Come back in 5 minutes before the hour. All right, we'll be right back. Left. We only have an hour left, so I'm going to have to skip right to the differential timing material, because the most important things that I think that you will learn today is the Andrew Goodman-Bacon paper and the Callaway and Santana paper. These are the two. If I had to just leave you in this workshop with two really important messages, it would be, how do you handle differential timing? All right, so let's just dive right into that, and I'll walk you through differential timing problems. So, you know, it was mentioned a minute ago, Arnold had asked, is the major drawback of two-way fixed effects whenever parallel trends fails? The major drawback of two-way fixed effects is actually how it handles heterogeneous treatment effects. The way in which differential timing, which is when you have more than one treatment group that's treated over time, how that is handled with how two-way fixed effects handles heterogeneity under differential timing. Put it differently, the problem with two-way fixed effects is simply that it doesn't estimate under differential timing with heterogeneity what we think it estimates. That's really it. And there were several papers that at this point, it's like a half dozen papers that use a variety of different forms of analysis to show what two-way fixed effects does and does not estimate. Andrew Goodman-Bacon is not the first one. It's actually by Borisak and Jaravel, 2017. But I read Andrew Goodman-Bacon first, so I typically teach it this way. I find it a very intuitive paper. So what we're going to do is two things, two ways to end the workshop. All right. One, Goodman-Bacon on differential timing and two-way fixed effects. Two, Callaway and Santana on differential timing and alternative estimators to two-way fixed effects, right? With code. All right, that's what we're going to do. This paper is now forthcoming in the Journal of Econometrics 2021, but I'm going to discuss the original paper. All right, so we know these 2x2 specifications. We discussed it earlier today. We've got here this 2x2 form of the post-treatment minus the pre-treatment, post-treatment minus the pre-treatment, and then we difference that difference, right? And when we have a 2x2 group, we have this specification here. We might put in covariates, put in our fixed effects, but really it's the interaction. But when you have differential timing, you'll usually just have a dummy for whether the treatment group is treated or not, or whether the unit is treated or not, because you really can't have an interaction with differential timing because you've got this multiple staggered. So you just, instead you have just a dummy for whether it's treated or not. And typically what we hope that two-way fixed effects will estimate at some kind of weighted average over all treatment effects in the D = 1 periods. That was our hope all along. Turns out that hope was misguided. That is not what two-way fixed effects estimates at all with differential timing. Even though that was what two-way fixed estimated in the two-group case. So, you know, it's understandable. It's understandable that we thought it would work because one, many of us are not econometricians, and B, it did work for the two-group case. The problems just were not well understood before this wave of papers over the last 4 to 5 years, right? So here is going to be what Andrew Goodman Bacon does. He is going to decompose the two-way fixed effects estimator into what it is estimating, which is going to be a weighted average over all 2x2s in the sample. That weighted average is going to have units functioning as both treatment and control group, and the weights are going to be based on sample sizes and the variance of treatment for the groups. Then what he's going to do is he's going to show you both what causal parameters are in that weighted average and what forms of bias there are. And he's going to show you that under the best case scenario, two-way fixed effects will estimate what's called the variance weighted ATT, which is a weighted average over all possible ATTs. Under more restrictive assumptions, it will perfectly match the average treatment on the treated. Time varying treatment effects are going to generate a bias that needs to be accounted for. Right. So let's look at this real closely. Let's look at it with a toy example. Let's say that we have 2 treatment groups, K and L, and 1 untreated group. K and L is going to define the groups based on when they receive treatment. K is going to receive it earlier. Sorry. Okay. K will receive it earlier than L. We're going to call this D bar. D bar will be the share of time that a group spends in treatment status. So let's say that, assume that K is treated in year 5 out of 10 years. Its D bar is 0.5 because 5 over 10 equals 0.5. Assume that group L is treated in year 7 out of 10. Its D bar is 3 out of 10 because it only spent 3 years out of 10 treated. All right. So its D bar is 0.3. Right. So that's what D bar is. D bar is the share of time a group spends in treatment, right? And then we've got our 2x2s. And the question is, if we have differential timing, that means we have more than one group, more than one treatment group. So this is no longer the simple two-group case. If two-way fixed effects estimates a weighted average over all 2x2s, how many 2x2s are there? Okay. All right, so let's look at that. There are a lot. Let's do it manually. Say that we have three groups, A, B, and C, and we have one untreated group, U. Then there should be 9 2x2s, because look, we can do a 2x2 comparing A to B, A to C, A to U. We can go B to A, B to C, B to U. We can go C to A, C to B, and C to U, right? So those are all of the possible 2x2s. So if you have more than one treatment group and one untreated group, you have K squared 2x2s, where K is the number of treatment groups. So if you have two groups, K and L, if you have two groups, K and L, then you have 4 2x2s. Now let me show them to you. Let me show you these 2x2s, right? So this right here will be group K. This is group L. And this is group U. And this is the outcomes here. This is the outcomes. And this is time. All right. This is time. And this right here is when group K was treated. This is K's treatment date. And this is L's treatment date. Okay, so we got K's treatment date and L's treatment date. And this is the pre-K period. This is the post-K-L period. And this is the in-between period. This is the period mid-KL is the period between when K was treated and L was treated, right? Okay, so notice, oops. Okay, so we've got this group U. Notice group U just gently increasing in value, right? Just gently increasing in value. And group K, group K, oops. Gently increasing in value. Then the treatment occurs. Then it increases again. Group L, gently increasing in value, rises, keeps going, right? So that's all that's going on here. All that's happening with this is just a picture demonstrating changes over time, all right? There are 3 2x2s associated with that picture. Let me show them to you. Here's one. This is the K to U 2x2, right? K to U 2x2. Let me draw it. All right, so here's the post K. Here's the pre-K. Here's the post L. Here's the pre-L. All right, and then we'll just draw it out. Okay, so 2x2 for KU. We're going to go, it looks like that's a 35 minus a 20 minus 10 minus 8. And that's going to be 15 minus 2. It's going to be 13. So the KU 2 by 2 equals 13. There is no causal interpretation here. This is just a number we calculated using that formula. All right. So we go to the next one. We go to LU. Right. LU is same thing. Okay, we go through, do all those calculations, we get a number. Then we get some K to L comparisons. We get some K to L comparisons, right? And the K to L comparisons are going to be, the K to L comparisons are going to be the comparison of group K with the group L. So that would be right here. There's the group K, mid period minus pre. And here is the pre, and you would just go through and you would do this. But here's the thing about that I want to bring to your attention here. Notice what is different with this 2 by 2. Group K treatment is being compared to group L, also treatment. But in this 2 by 2, group L is not yet treated. Okay, not yet treated. Remember that. Not yet treated and untreated. Group U actually are very similar kinds of groups for this DID analysis. Now this is another 2 by 2 that can be calculated. And this 2 by 2 is comparing, this 2 by 2 compares group L, treatment group, to group K, and already treated or earlier treated group. This one is special because of how bad it is. This is the problem with two-way fixed effects. Arnold asked, is the problem with two-way fixed effects the parallel trends assumption? No. Problem with two-way fixed effects is the mechanics of OLS in a DID design are such that this particular 2 by 2 will be implicitly calculated, and this particular 2 by 2 is bad. And it's bad, as we will show, because the treatment effect is operating inside that YK outcome. And that will cause distortions in our numerical calculations of some treatment effect. It will cause distortions. So what exactly is the diff and diff estimator? The least squares estimate of a difference in differences design with differential timing will calculate a weighted average over all 4 of those 2 by 2s. Okay, and where are they? Here are the 2 by 2s. Inside this 2 by 2, there's the KU and there's the LU. All right, so it's basically 2 of them. There's two 2 by 2s here. KU, never treated, and the LU, never treated, right? So we've got this weighted average, or we've got this 2 by 2 here, and then this one is comparing to a not yet treated, okay? And this one is comparing to an already treated, all right? So got the two of those there. And then we have these weights. Oops. All right. And so you have these, you have two forms of weights here. You have these population level S weights, and then you have these mu weights. Okay. And the S weights sum to 1. They modify both the never treated 2x2s, and they modify the treatment group controls 2x2s. Okay, the mu's are also separate set of weights. So let me just say one thing. Something that surprised me when I was studying the DID papers of the last few years is that nearly all of them are focused on the implicit weights that OLS calculates in a DID specification. So many of them are about weighting, it turns out, is a major part of the new papers on DID, right? And here you see the weights right here. So a lot of the papers are trying to understand how that weighting works. And part of it is that with differential timing, we can get negative weights, which I'll show in just a moment. We can get negative weights. And negative weights make it difficult to interpret things in causal ways. All right, so here's the weights. Here's some of the weights in the decomposition. So what you've got is NK and NU. All right, NK and NU. And what N is N is the share of units in the treatment group or the control group or the never treated group. Okay, so if there are 50 states total and 20 are in the treatment group, then NK equals 20 over 50. All right, that's what it would equal. And NU would equal 30 over 50. So 60% versus 40%. All right, so you get these weights on the share of units in the treatment group or the control group. And then you get this D bar. What I've seen so far is that it's the control group that gets released to treatment. And they do two-way fixed effects as late. Melba, I don't understand this question. I'm not familiar. I don't know what released means. As do two-way as late versus. Are you talking about this, Melba? Is this what you mean? Where the control group here is a group that's already been treated? Is that what you mean? That I mean, two-way fixed effects is basically calculating a weighted average over all four of these 2x2s for the two group for the differential timing scenario with two treatment groups. That's what it's doing. So you're not manually doing this in any sequence, OLS does this implicitly. It calculates each 2 by 2 and then weights according to those weights and adds them together. I'll show in a simulation that it actually is exactly this. It's actually exactly this. Oh yeah, right. In the post-L period, no group remains untreated. Well, technically, in the post-L period, group U in this example is not treated. Group K and L are both treated. But in this scenario, we have this never treated group. Okay, so you can see right here, group U still not treated. So you can still have with differential timing, you can still have groups that are never treated. Okay. There are situations where everyone is treated though, is treated eventually. I'll do that in the simulation. But all that will mean is that one of those 2 by 2s will never exist. This one. So if everybody is eventually treated, then that won't exist. And all that OLS will estimate is a weighted average over treated to not yet treated, treated to already treated. Those will be the 2 kinds of 2 by 2s under staggered adoption. But if there are units that remain untreated at the end, then those will also be calculated, and weights will be applied to those. Does that make sense, Mo? Okay, good. All right, thank you. All right, so we got these weights here. It's the share of units that are in the treatment group or the control group. And this is the share of time that a group is treated. All right. So let's look at this one right here on the next slide. This is D bar times 1 minus D bar. So we've got here the SKU weights. These are the never treated weights. And these are these not yet treated weights and the already treated weights. Actually, this is just the treatment control weights, right? Yeah, because it's on the outside of the whole thing. And then this is the interior weights, right? So you get this never treated weights. And what I want to talk about right now is this. All right, let's talk about that on the next slide though. So the 2 things that I want to emphasize though inside these S weights, 2 things I want to emphasize inside these S weights is you've got this. And you got this. Okay. So you've got here 2 pieces of the S weights. 1, share population in a group. 2, share of time a group is treated. All right, those are the 2 pieces to it. So we go to the next slide. Right, we see that 2 things pop out of these weights. Group variation matters a lot. That's this part right here, share population in a group. Group variation matters a lot. A group is if 2 states get treated at the same time. So one of the weights that matters is the share of units that are in a group. The other thing that matters is the share of time that a group is treated. And the expression on it is this. So let's think about what causes the treatment variance to be as big as possible. Let's say that you spent 10% of the time. So I'll draw this. Okay, so we have this right here, and this would be year 0. This would be year 9. So 10 years, 10-year panel. Okay, so let's say that we have year 1, year 5, year 8. All right, year 1, year 5, year 8. So D bar 0.1, that would be right here. That'd be a D bar 0.1, because they're only going to spend, they're only spending this much time in treatment, and they're spending, you know, this much time in the control. So they're only spending 0.1, 10% of the time treated. All right. Versus, you know, this much time untreated and this much time treated. That would be a D bar. That'd be a D bar for that group of 0.5. That would be for this group right here. And that would be for this group right here. And then we have this last group here. Let's see. So that would be, they're spending all this time treated. They're spending this time untreated. So we have a D bar of 0.9 because they're treated for so long. So we just put that, give them a 0.9. All right. So you've got these like different kinds of groups. All right. And according to that that expression right here, D bar, this right here is called the variance of treatment. That's called the variance of treatment right there. All right. So how big does the variance of treatment get? All right. Well, let's look at this one. Say it's this guy right here, 0.1. That variance of treatment is going to be 0.1 times 0.9, because the equation, remember, is D bar times 1 minus D bar is the variance of treatment. D bar times 1 minus D bar. So you get this 0.1 times 0.9. You get a 0.5 times 0.5. You get a 0.9 times 0.1. Right? So you got all these expressions all along this line, okay, is a variance of treatment. How big does it get? Well, at for the 0.1, it'll be 0.09. So that right there will be 0.09, 0.1 times 0.09. Anybody that's at the 0.4, that would be right here. Okay, that'd be right there. That'll be a 0.24, 0.4 times 0.6. This one will be 0.5, okay, times 0.5, that'll be a 0.25, and then it only gets smaller. So if I was to calculate, this one, this 0.4 times, this would be 0.6 times 0.4, and this one is 0.4 times 0.6. Well, notice this one right here is a 0.24, and that one's a 0.24, right? You can see it right here, right? 0.4 times 0.6 is 0.24. So that's a 0.24, that's a 0.24, and that's a 0.25. Well, what this means is it means that D bar okay has a max. And that max is at 0.5. That max is at 0.25. Okay, that max is at 0.25. Now, what is that? What is the implication of that? So a couple of things I just want to say. The largest that the variance of treatment can be is 0.25. But that only occurs for units whose D bar, share of time treated, is 0.5. So what? This means that OLS is going to place the highest weight on those units who are at the middle of the panel, who are treated at the middle of the panel. Go back to what we just did a minute ago, right? So you have this 9-year period. This is year 0. This is year 9. And I've got this here, here, and here. Okay. So this is group A, group B, and group C. And this has a D bar of 0.8, 0.9. This has a D bar 0.1. This has a D bar of 0.5. Two-way fixed effects will place the highest weight on group B's 2x2 when calculating that two-way fixed effects number. Units, OLS favors the units in the middle of the panel with respect to treatment dates. And there's nothing necessarily theoretically attractive about that. There's nothing necessarily theoretically attractive about that. Okay, so what about this treated on treated weights? Same thing. I'm not going to talk about it. So only have 30 minutes, so I probably better hurry. So groups in the middle of the panel weight up their respective 2x2s via this variance weighting. There's no theoretical reason to prefer this. It's just a weighting procedure being determined by how we drew the panel. So this is the first thing about two-way fixed effects that should give us pause. Not all estimators do this. What we're going to do now is we're going to take those 2x2s and we're going to put them in terms of their potential outcomes. All right, so here's the KU 2x2. It equals ATT plus selection bias. This is basically no different than what we did at the beginning of the day today. We just substitute 2x2s into their causal effects and their selection bias. KU is like that. KL is like that. All right, so KU has a causal parameter, has a parallel trends assumption. KL has a causal parameter, it has a parallel trends assumption. And then LK has a causal parameter, a parallel trends assumption, and this third thing. And this is what I want to emphasize here. The 2x2 associated with comparing a treatment group and an already treated group, when estimated with two-way fixed effects, has an additional bias other than parallel trends. It is the heterogeneity bias. It is the heterogeneity bias, right? When calculating this 2x2 implicitly, it is not equal to the ATT under parallel trends if treatment effects are changing over time. That's that second form of bias, right? So the main problem with two-way fixed effects is that because it implicitly calculates a 2x2 comparing treatment groups to earlier treated units, if those earlier treated units have dynamic treatment effects in them, then that 2 by 2 will have additional sources of bias, both parallel trends and heterogeneity bias. It's really heterogeneities in treatment effects that two-way fixed effects does not handle well without adjustments. You have to somehow adjust for it. So then what we're going to do, is we're just going to plug these in here. Okay, so we're going to plug all of these terms here into that weighted decomposition. All right, so we're going to replace the raw data with the in this decomposition with their corresponding causal interpretation and biases. All right, we're going to do that, and then we'll just rearrange it into something sensible. And this is what we get. When you estimate a difference in difference model using two-way fixed effects, and there is differential timing, then the two-way fixed effects parameter estimate is equal to the sum of three terms: causal parameter, parallel trends bias, heterogeneity over time bias. All three of them summed together. Okay, and what you need in order that two-way fixed effects be unbiased estimate of the ATT is parallel trends, no heterogeneity in the dynamics. Only then will you get the variance weighted ATT. Let's see if we have time. So it's 9:37. Yeah, I think I got to show you this. So, so if you go into Causal Inference Workshop, then you go into master do files, there's a program called baker.do. All right. And baker.do is a simulation that is going to illustrate the bias of two-way fixed effects. All right. So what I'm going to do is I'm going to generate a fake panel. All right. So it's going to be 30 years of data. Right. It's going to be 30 years of data. Count 30,000. There's going to be 25. There's going to be 40 states. Sorry, 40 states, 25 firms per state over 30 years. It's going to be 30,000 observations. I gotta get rid of all this stuff. Okay, sorry. Okay, now we're going to do the differential timing. So I'm going to have 4 groups. Okay, 4 groups. Group 1 is going to get treated in 1986. Group 2 is going to be treated in 92. Group 3 in 98. Group 4 in 04. All right, so I've got 4 groups, each of which are treated, each of which are 25% of the sample. All right, then I'm going to have a simple data generating process such that it satisfies parallel trends. All right, so I'll have that done here, and I'm going to say you're in the treatment group. TE group 1 is going to get a treatment effect of 10. TE group 2 is going to get a treatment effect of 8, 6, and 4. All right. Okay. So let's generate a treatment effect. Let's generate a treatment effect. I'm sorry. Let's generate outcomes here for 2 situations. One with constant treatment effects. This here is constant treatment effects. Each group is going to be treated, dummy. Right? So each group is going to be treated, yes or no. And then they're going to be treated with a treatment effect of 10, 8, 6, or 4. Oops. Oh, yeah, I can't. Sorry. It's here it is. 10, 8, 6, 4. It's got a little variance in it. I put a little bit of my friend Andrew Baker is the one that did this, but he puts a little bit of some variation in there. All right. And then what we're going to have here is the dynamics. We're going to put the dynamics into this. Okay, we're going to put some dynamics into this. And what this means is that for every additional year that it's treated, for every additional year treated, that's that year minus treat date plus 1, the treatment effect increases, right? So if it's 1986, this is 1986 minus 86 plus 1, that'll equal plus 1, and TE equals 10 times 1, 1986. So in 1986, treatment effects are 10, 1987, treatment effects are 20, 1988, treatment effects are 30, and so forth. All right. So what I'm going to do is I'm going to estimate the treatment effect. I'm going to put this right here. I'm going to estimate the treatment effect on my treatment dummy using the constant treatment effects. Now, I know that there is a treatment effect of 10 plus 8 plus 6 plus 4 divided by 4. So that's going to be 10 plus 10 is 20, 28. So that's going to be 28 over 4. That's going to be a 7. So with constant treatment effects, the ATT is 7. Will 2A fixed effects yield a 7 on the coefficient on treat? And it did. It got a 7. Okay. Now let's see how it handled dynamic treatment effects. Let's estimate that one. All right. Now remember for a second here, notice, keep in mind, all treatment effects are positive. All dynamics are positive. You can see that because look, see how these right here, those are all positive numbers, and that's positive. Okay, so they're always positive. All the treatment effects are positive. But think back to the representation. Think back to the representation of oops. Look real closely at this. All right. So let's say that this was a 5. Okay. The variance weighted ATT was a 5. Let's say that common trends holds. Well, let's say that the dynamics are a 10. All treatment effects are positive, but 5 plus 0 minus 10 is negative. So here's a risk. If those dynamics are large enough, relative to the variance weighted ATT, the sign can flip. Okay, the sign can flip. Let's see what happens. Negative 6.69. We know that the treatment effects are positive because we mechanically built it to be positive. We mechanically built it to be positive. But the problem is two-way fixed effects will take weighted averages over all those individual 2x2s. And if there are any dynamics in the treatment effects over time, then it will skew that calculation. Let's look at this a little bit more carefully. If you go back to the slides, you have this right here. Okay. Now, this is the decomposition of the two-way fixed effects estimator, right? You can decompose the final number, which was negative 6.69, into weights, 2x2s. Okay. Well, those can both, the weights are based on N and D bar, which can be estimated with data. And the 2x2s are based on Y, which can be, which can also be calculated. So we can actually calculate, we can actually manually recreate this decomposition ourselves or with software. Let me show you the software. So there's a command in Stata called DD timing, all right? And I'm going to run that regression again, the one that I did on the differential timing. There it is, negative 6.69. And then I'm going to do DD timing. I'm going to do DD timing. I'm going to basically do the outcome on a treat. I'm just going to decompose that treatment variable treat into its different parts. And look what I get, right? So I get half of that calculation right here. Half of that calculation is coming from comparing earlier treated groups to later treated groups. Now these right here are not problematic. Okay, so this one right here isn't problematic. But this one, that one is problematic. Okay, this one is problematic. This one is problematic. It is the source of bias because there are dynamics built into the treatment effects. And this is the only source of bias associated with dynamics. Okay, so watch. This negative 6.69, 0.5 times 51.8, 0.5 times negative 65.180, negative 6.69, negative 6.69. That negative 6.69 is just coming from a weighted average of each of these individual 2x2s. Okay, each of these individual 2x2s. We get to the end of this. So real briefly, what can you do? What can you do? Well, there are now probably a half dozen new estimators that you can estimate that will handle that heterogeneity just fine. that'll handle that heterogeneity just fine. And the one that I want to introduce you to is the Callaway and Santana estimator. There are others, okay? There are others. And based on my review of these papers, once we have solved the main problem, which is that one particular 2x2, once we have solved that main problem, many of them are getting at the same answer with slight differences, okay? With slight differences. And so I'm just going to present to you Callaway and Santana because it's based on that Abadier paper. But if you come to my my Cholera class that I'm doing on the 23rd, it'll be if you look at my Substack. Let me show you real quick the Substack. If you go, no, I have I will be doing a workshop on difference and differences. It'll be 3 a.m. for me, but it'll be 10 a.m. for you. You're welcome to come. It'll probably be about, it's probably going to be all day. It's going to be an all day kind of thing, but I will take you through all of the new papers. I will take you through the world of difference and differences of the last 5 years that I hope will, you know, prepare you to do this kind of research with differential timing. But let me just show you Callaway and Santana for now. All right. So Callaway and Santana are going to consider a model with multiple time periods, which is really common, differential timing, and parallel trends, right? So basically with or without observables, all right? With or without covariates, okay? Now, what they're going to do is rather than just write down a regression equation and hope that the coefficient equals something we are intuitively searching for, Callaway and Santana will write down precisely an expression for the causal parameter they care about. They call it the group time ATT, right? They call it the group time ATT. Once they have defined that parameter, they build an estimator that unbiased, that without bias estimates that parameter. They then propose weighting procedures to get the overall ATT, okay? They then propose weighting procedures to do that, all right? So what is the group time ATT? Groups, cohorts of units treated at the same time. They're going to calculate an ATT per period. So let's say you have, let's say again, it's a 10-year panel. Group K is treated in year 5. There is a year 6 ATT for K. There's a year 7 ATT for K. There's a year 8 ATT for K. There's a year 9 ATT for K. There's a year 10 ATT for K. Okay. They are proposing calculating a group time ATT for every group for every period. That's a lot of parameters. Definitely more than the one parameter we were estimating with two-way fixed effects, right? So it's definitely more than that. Okay. Now, before we get to what we're going to do with it, let's just go ahead and calculate it. Okay. So parallel trends. So here's the notation. We're going to have T periods. Units are either going to be treated or untreated. Group G is going to signify that a group is, it's going to signify that a group, Group G is going to signify which group you're in. Capital G is going to be a dummy for whether or not you're in a group. Lowercase g is going to signify the year that you are treated. All right. C is binary. It will indicate that you're in a not treated or a not yet treated group. And then we're going to have that propensity score again, right? The propensity score. So they're going to estimate that propensity score. So when are you going to do this? If you think you have heterogeneous treatment effects, if you think treatment effects change over time, that's when you're really going to use this. You use these robust estimators for DID if, one, you have differential timing, and two, you think you have heterogeneous treatment effects, right? You're just going to, from now on, you're going to skip two-way fixed effects, because the problem with two-way fixed effects is it is not robust to heterogeneous treatment effects if there is differential timing. So you can't afford to use it. It is, as we saw, even potentially the wrong sign. Okay, so you cannot afford to use it. You've got to go directly to a robust estimator like Callaway and Santana. So here are the assumptions that are needed for Callaway and Santana: panel data or repeated cross sections, conditional parallel trends. Here's that parallel trends assumption. Treatments have to turn on. They cannot turn on and off. So there's a different estimator out there by DeChaseman and I can't pronounce the last name. And they have one for reversible treatments, common support. So it's really a lot of the same stuff we saw with the Abadier. With the Abadier, we saw this one. We saw this one. This was also I kind of skipped that. And Abadier was only focused on 2 periods, so there was no opportunity for treatments to reverse. And here is the estimator. All right. Notice how similar it is to Abadier's estimator. Okay. So you have over here this, oops. You have this difference. All right. You got a dummy for whether you're in the treatment group or whether you're in the control group. Now, if you're in the treatment group, then that's a 0. And all you'll do is you'll take that first difference and you'll weight it by that share. All right. Just like we did before with the Abadier. But if you are in the control group, that's a 1 and that's a 0. And you'll weight that first difference. You'll weight that first difference by this ratio of propensity scores. Which units will and will not be used as controls? Notice the C is referring to the control group. And you are not going to be using, you're not going to be using already treated groups in your controls. So Callaway Santana are restricting, Callaway and Santana will not let the already treated units be in the calculation. C will equal 1 for not yet treated or never treated. But the already treated units are discarded. Okay, they are discarded. And then they'll propose a bootstrap. All right. So let's look at real quick, just a simple, let's look at a simple version of this estimator. Right. There's a few things we need for this estimator. Right. We need dummies for groups. We need propensity scores. We need to calculate outcomes. And then we just got to weight. All we're going to do then is just weight each of these outcomes. by these weights. All right, so let's do it. And then I got to let you guys go. All right, so let's get our dummies. So we get our dummies. Check. Then we get our propensity score. Check. Okay, I got my propensity score. Then I calculate my post and my pre value of y. That's calculate this, calculate this. Right? So I did that. Now I've got to calculate those denominators. Whoops. So I've got to calculate this, and then I've got to calculate that denominator. So I did that here using commands in Stata. There's commands in R that'll do it too. Then I calculate my weights. There's weight 1, there's weight 0. So I'm going to calculate those weights. And then I'm just going to weight these observations by each of these weights. Okay, and then I calculate, look at this. So now what I do is I calculate, that right there is the difference in difference expression. It's just that I'm using weighted observations. Now remember, go back up here, right? In 1986, okay, in 1986, group 1986 had a treatment effect of 10. You can see it because this was a 10 times a 1, because that right there turns out to be a 1. All right. So let's see if we get a 10. We get a 10. Let's do it again. We know that in 1987, it should be a 20. Let's see if we get a 20. We get a 20. Okay. Now, manually doing this in Stata obviously is not desirable. So what I've done down here is, where'd it go? There it is. I have written a lengthy Substack here for those of you that want to see this. And at the bottom of this Substack is the R code. And you can do this yourself in R. You now have the ability to estimate the Callaway and Santana estimator in R. And any day now, it's going to be available in Stata. There's actually a beta version that just came out this week in Stata. So you can estimate the Callaway and Santana model. And what you can do with the Callaway and Santana model, you can estimate those overall, you can estimate each individual group time average treatment on the treated, and you can also combine them to get the weighted averages that you care about. Okay. So I unfortunately ran out of time. So I just want to end there by saying that, let me get to where I was going to end it. Concluding remarks. Chances are you're going to write a lot of papers using difference and differences. There's going to be more difference and differences papers probably you're going to write, more than any other paper. And there's a lot of new literature. So I wasn't able to get into the full literature today, but I will be doing a free workshop on difference and differences on the 23rd for Africa, or rather for the non-America. I'm doing one for the America countries on the 16th, and then a week later on the 23rd. You're more than welcome to come. It's free. You can just come, you can attend, you can learn some of these papers. I'll be walking you through code. I hope that it's a useful exercise. But if you only hear me say one thing today, that is that with differential timing, two-way fixed effects is flawed. It can't handle heterogeneity, not without additional adjustments. Now, the problem is not two-way fixed effects. The problem is those implicit comparisons that two-way fixed effects does to compare it with already treated units. Angelica asks, how do you enroll? Angelica, if you'll just go to, you don't have to enroll. There is no enrollment. If you go back to, here, if you just monitor, if you'll, Angelica, actually, if you'll just go to this, if you'll just go to this website and subscribe to it, if you'll just subscribe to this newsletter, you'll get the updates. It's free. It's a free workshop. It will all be streamed from Twitch. So all you got to do is follow this account, causalinf_DID, and I'll be giving instructions along the way about how to get ready, but it'll just stream. And all you'll have to do is just sit here and watch it. And I'll provide some help for you to know how to ask questions. The questions will show up to me on the screen as I'm talking, and I'll just stop and answer your questions. Now, there's going to be 3,500 people at this conference, but in Africa, it'll be much smaller is the sense I get. So I think that the Africa, Europe, Asia, Australia workshop will be smaller, although I don't really know. Okay. For the long panel, Panya, yeah, for the, that's a long answer. There's a long answer to that question. So if you have groups that are moving into and out of treatment, it kind of depends on exactly what you're describing. If you've got groups in the control group that are sort of moving into treatment, independent of the treatment assignment itself, they're kind of doing it, they're like going to college, not because of the program, but because of some other events. There's a design called the fuzzy difference in differences that you can use. I discuss it on my Substack, but if you've got a long panel and treatment is turning on and off, so some states are getting treated and then treatment's turning off, there's another estimator that you have to use. So I'm going to discuss all of these at the workshop. So when do you use the doubly robust DID? Arnold, you use it as an alternative to Abadier. So that's what I didn't get into today. The doubly robust difference in differences is basically a combination of the Abadier estimator and this estimator by Heckman. And essentially what it is for situations where you have covariates, but you're not really sure if you've modeled the propensity score correctly. It's like it's a way of controlling for covariates in two different ways so that you're not stuck having to commit to that propensity score model. There's and I actually discuss it, Arnold, if you look at my Substack, right here, the tale of time varying covariates. This is about the doubly robust. So it goes into detail about the doubly robust and can kind of explain it about when to do it and why it works. But I'm sorry, I couldn't, it's just that, like I said, the Coachella concert that I'm doing this summer is probably going to be about 8 hours. So it's just not possible to cover everything. I just wanted to give you a flavor of the problems of two-way fixed effects and one of the solutions. But just kind of to conclude, I think that what I would conclude with is I would say that, in 2021, it's a world in which journals are expecting you to know these methods, to know the econometrics, to know the art of causal inference using natural experiments under randomization and non-randomization. And the amount of material that you need to know is very large. And that's why these workshops are offered, is to try to get you up to a new level that you feel a little bit more comfortable and going to the next level. So that Coachella concert is kind of a little bit more advanced. It's a little bit more advanced and should empower you to feel even more comfortable afterwards. Okay. So that's all I want to say. I want to say thank you for letting me talk to you this week about causal inference. I hope that you found it useful. My book covers a lot of this material too. It's free. It's on my website. It has some errors, but in the physical book, but the online book has been correcting those errors as they are discovered, and the new versions of the book will have those errors taken out. Okay, so thank you so much. And I see that you want to take a photograph. So thank you so much, everyone, for having me.